Hello everyone, I'm Rancho and I'm very glad to share my research with you at the Black Hat Europe conference. My talk today is Discovery 20 Years Old Vulnerabilities in Modern Windows Kernel. As the title shows, this presentation will talk about an old and well-known component in Windows kernel. It's named User Mode Print Driver (UMPD). Actually, I have got more than a dozen of bugs from the UMPD callback. But Microsoft just merged 9 cases of them. In fact, these bugs affect all the versions of Windows system from the Windows 7 to the Windows 10. It is still very few people had paid attention to the security issue about the user mode print driver. So I want to discuss the details about the UMPD callback with you. Okay, I will give a brief introduction about myself. I am a researcher of Singular Security Lab. Past years, I mainly focus on Windows kernel bug hunting and exploitation. And I have also found some bugs about virtualization in VMware Workstation and Microsoft Hyper-V. And in the past, I have spoken in several security conferences, such as HITB, 44Con, and Zero Nights. The agenda today includes 3 parts. First, I will introduce the print driver model in Windows system. The second, I will introduce the UMPD callback and display why the user mode print driver could lead to a good attack surface. The third part, I will disclose 2 bugs found by myself, which never discussed by others before. Okay, let's have a quick view of the printer driver. From the Windows 1000 systems to now, all the Windows printer drivers consist of mainly 2 components: the printer graphic DLL and a printer interface DLL. A printer interface DLL usually provides a user interface to the driver and provide an interface the spoiler could call to notify the driver about the print system events. The printer graphic model usually assists GDI kernel in rendering a print job and send the rendered data stream to the print spoiler. This picture shows how the printer graphic model working with the GDI rendering engine in kernel. A printer graphic DAL should implement the graphic device driver interface to ensure that its graphic device produces the valid graphic output. The graphics driver interface function is named with a prefix drv. Some of the driver interface functions listed below. As you see, if you start a print job, we'll execute the drv start doc, drv start page, drv start binding functions in the user mode print driver. And when the kernel drawing the graphic images, the drv bit build, drv fill path function should be called. When a user prints a document and start rendering a print job, the interaction between GDI render engine and the printer graphic driver as follows as shown. We can see that the GDI kernel called drv enable surface function in print graphic driver attack the UMPD callback. The second part of this talk, I will introduce the working mechanism of user mode printer driver in depth. What is UMPD? It means user mode print driver. As the original design of Windows system, print driver models are loaded into the kernel. But started with Windows Vista, Microsoft made a big change. The printer drivers would run in user mode instead of running as part of the kernel. This change was made as a security enhancement, and the security benefit is quite clear. Once moved the printer driver into user mode, the bugs in printer driver have a much reduced security impact. In fact, it truly reduced the bugs in the printer driver, but it had create a new attack surface to make the graphic kernel more dangerous, because the kernel callback should call back to the user mode print graphic driver. A user mode printer driver should export the driver interface functions. These functions named with the drv prefix. They will be called by the kernel GDI engine. The callback from graphics kernel to user mode print driver could lead to a big attack surface. As you know, the kernel attacks through the user mode callbacks. It's a very good presentation. The user mode callback is first discussed in public 9 years ago. We just reviewed Win62K user mode callback vulnerabilities. A classic user mode callback bug is shown as this. When you create a user object in user space and when you trigger some functions to call a user mode callback to user space, and the attacker the attacker could hook in the user space to modify the object. And when you return to the kernel code reuse the object. It could make many security issues. Through the user mode callback, vulnerabilities has been discussed many years, but few people ever noticed that the UMPD callback functions. As shown in the left, the UMPD driver prefix functions. Let's look how the UMPD driver functions triggered a user mode callback. All the UMPD driver functions in Win62K will call the UMPD obj stack, and the UMPD obj stack called PPP user mode callback finally. The PPP user mode callback function returned to the client printer stack in user space. The code of UMPD obj stack function passes the parameters directly to client printer stack function. But if current process is a 32-bit process, the UMP obj stack will send a local procedural message to a proxy port created by the printer driver host. By the print driver host process, the SPLOW64. This process is the print driver host. It is created for the 32-bit process using the print driver. The communication between print client and the print driver host could also make a big attack surface too. It is another story about Versa sandbox escape. Let's come back about the UMPD callback. As you see in this page, the call stack, the typical user mode printer driver callback stack like this. It is difficult for others to notice these specific flaws. Why? I think three reasons. First, the UMPD driver functions are not referenced directly in the kernel's code, so it is not easy to find them. The second reason, the UMPD driver functions not use XXX or ZZZ as the name and the prefix as function name. The previous researchers told us the XXX functions will trigger user mode callback. Maybe we just not consider the other situations could also trigger user mode callback. The third reason, The third reason, we need to meet certain conditions for triggering the UMPD driver functions. If the thread is not a UMPD thread, or if our code haven't implemented the specific driver interface function, the graphic kernel will not execute the UMPD driver function. So, how to trigger a UMPD callback? Shall we implement a print driver for ourselves and register it in system? No. We could just use the virtual printer created by the system, such as fax, XPS document writer, and OneNote. Case study. In this part, I will discuss two bugs found by myself. The CVE 2020-0887. In fact, Microsoft merged 9 cases I reported last year. One of them is the GREEXT text out wlocked function user-free. The root cause shows here. The specific flaw exists within the GREEXT text out wlocked function. The issue results from the lack of check for the surface object in printer device context. When the GREEXT text out wlocked function called the UMPD text out function, as you know, triggered a UMPD callback. It will trigger a UMPD callback to the DRV text out function in the user mode printer driver. And we can destroy the surface object in user space. So we cause a user-free when returned to the kernel code. First, we create a printer device context. After that, start doc will force the printer device context create its surface. Then the text out function will trigger a UMPD callback to DRV text out. Now we just need hook the DRV text out function in NXDW driver. When we call endDoc function in our redefined DRV text out function, the surface selected with device context will be destroyed. Now the ESI register point to a freed pool memory. The crash stack shows as here. Let's look at another case, a little more complicated. In this case, we should modify the data returned by the original UMPD functions. First, we initialize a user mode printer driver instance, and we start the doc to create the surface with device context. Then the next, we call anti-GDI2 binding function. In the kernel code, the GRE2 binding function will check the return value and the point X and the point L structure. So we should modify the X field of point L structure and return true in our hooked DRV next band function. If we enter dog in our DRV next band function, the surface object associated with the printed device context should be free. It will lead to a use of free. Conclusion. I think I can share my takeaways from the research. I think the people may not really understand what they use every day, such as the print driver. Second, maybe in some ancient components in modern system, you could discover some novel and unique vulnerabilities. As you see, we can find a new attack surface in some old code. At last, I believe the game with UMPD callback is not over yet. For example, this call stack shows an out-of-bound memory write in kernel after we have modified a padded object in our redefined UMPD driver function. This bug is patched already in April this year, but I'm not sure which CVE number is assigned for it. The last case, it is still a 0-day. It's a non-point reference in WinC2K kernel. The Xclip object is destroyed already in my redefined UMPD driver function. Yes. When the UMPD callback returned to the kernel reused the Xclip object. But in the latest Windows 10, the WinC2K will zero the free memory from the GDI object. When a GDI object is destroyed, the free memory will be zero. So it's just a non-point reference now. Thank you everybody. Thank you for your attention.